Hi everybody, this is the recorded version of GC Surgery Session 7 about mole percentage and data comparison. What we're going to talk about here is how we actually get the mole composition data and compare it in between GC, in between mole composition of one GC against its multi-level calibration composition, comparing it against the spot sample, etc. So to begin with, the question is, why do we do a comparison of the data? First is we compare the data to ensure that the GC works within its tolerable limit. And then we compare the result also to validate the pressure letdown system or the spot sample result by comparing the spot sample result against the GC data. And also we compare the result against the multi-level calibration results that we have to design a proper calibration gas composition that fits for the pipeline composition that we actually measure. And also to determine the risk from nonlinearity, which happen a lot if the design of the calibration gas is not suitable for that particular application. So where do we do the data comparison? So the first one is on the repeatability test. So what we do here, we basically take calibration gas and enter the calibration gas into the GC as an unknown gas, and the GC will rate the calibration gas result, will analyze the calibration gas, and then the analysis result from the GC will then be compared against the calibration gas certificate. So what we would expect from here is that the comparison between the two results will fall within a certain tolerance limit. The second place where we do the comparison is the reproducibility test. And for example, we compare a spot sample result against the GC reading. So what we do here is we basically measure the same gas with two different methods. One of them is by taking spot sample and analyze it with another GC somewhere else in the lab. And the second method is taking the sample and fit it in straight to the GC. Now the result from the GC reading will then be compared against the spot sample result. And again, this has to fall in within a certain tolerance limit. The other place where we do comparison is where we have two GC measure the same gas. So if we have a pipeline that is measured by 2 GC, normally is a duty standby GC, normally it's in the export line, it will be a good idea to compare the result between the 2 GC. So this 2 GC will have to fall in within a certain tolerance limit as well. And the last bit where we do the data comparison is to compare between the single point calibration mole composition versus the multi-level calibration mole composition. And this is very useful exercise actually to make sure that the calibration gas that we use is appropriate for the particular pipeline composition. A wrong calibration gas design will result in quite a significant bias that will impact the measurement. How do we compare them? All the data comparison needs to be done on normalized basis, such as repeatability test, reproducibility test, and then also comparison between 2 GC measuring the same gas. All of them needs to be done on a normalized basis. If we take the unnormalized basis, what will happen is that the 2 GC, let's say comparison between 2 GC, GCA will have a certain unnormalized total and GCB will have a different unnormalized total. The result will be quite significantly different. And a good result may actually be mistaken for a bad result because we're actually using the unnormalized total. So this is the example of why we normalize it. This is an example between GCA and GCB that actually have the same exact component, but GCA has an unnormalized total of 98% and GCB has a normalized total of 102%. So you can actually see that the tolerance fails pretty much on most of the components on the comparison. However, when we normalize them, it's actually the same exact gas composition. This is hypothetical data, just to show the impact of the use of the unnormalized total when we actually compare the data. So the only time we compare data on the unnormalized basis is when we compare the multi-level calibration composition or component against a single point mole composition. The reason why we use the unnormalized basis here is because we're actually using peak area to determine each individual component's bias. So the peak area actually work based on the unnormalized value of the composition. So that's why we have to work on the unnormalized basis when we compare multi-level calibration against a single point calibration mole composition. So let's start talking about each individual task that we need to do. The first task here is the repeatability test. So repeatability test traditionally done on a periodic basis. A lot of places actually do repeatability tests on around once a month. And the way repeatability test is done is normally done between 2 to 5 runs, and the tolerance is normally based on the ASTM D1945 standard. A lot of times repeatability test fails because it's done on unnormalized basis. Now here's an example. So we did a 40 hours repeatability test, and the chart that you see here is the chart on methane. As you can see, methane in normalized basis shows very good result. As you can see here, this is the tolerance, the high tolerance, high limit, and this is the lower limit of the tolerance, and methane sits pretty much bang on in the middle. So when we actually take the unnormalized result of methane, we can actually see this is the same exact data, but on the unnormalized basis of methane. So you can see that on the unnormalized basis, a lot of methane component will have failed the repeatability test. Now, it doesn't take a lot to actually fail the repeatability test. As you can see here, the unnormalized total composition, the maximum number is around 100.35% and the minimum is 99.6%, which falls within a very acceptable limit. When we take acceptable limit between 98% to 102% of unnormalized total, this particular range is really acceptable. However, it's actually enough to make the repeatability test fails on a normalized basis. So when do we need to do the repeatability test? With the life uncertainty method that we described in the GC surgery session 4, we don't really recommend periodic repeatability tests anymore, because if you actually monitor the data at all time, you basically have a feature called uncertainty, life uncertainty, and with a good low uncertainty, we will basically have a good reproducibility of the calibration result from the GC. Now, good reproducibility in the long-term period will mean good repeatability when we actually test it in the short-term period. That's what I was saying before, that low uncertainty means good reproducibility, and which means good repeatability. So, but repeatability tests is also have some place. It's still recommended in some of the scenarios. Some of the scenarios that we need to do repeatability tests are valve overhaul, column change, detector change, factory acceptance test, site commissioning. Basically, every time you want to start up a GC, for instance, we need to make sure that the GC will work correctly throughout the time in the future. So every time we do something big to the GC, such as changing diaphragm on the valve, changing column, a newly installed GC, we need to make sure that the GC will work properly after the installment. So one of the ways to do that is basically to perform a repeatability test. So therefore, repeatability tests still have its place to be performed. Now, the second place where we do data comparison is the spot sampling versus the GC reading. So it's basically a reproducibility test comparing the same gas with two different methods. So what we have now is a method to ensure that the GC works correctly. So if we know that the GC works correctly, that means we can actually use the GC reading to validate something else. So what we then do is we can take a spot sample result and then we compare it against the GC reading. So what this provides us with is a validation tool of a pressure letdown system. So if we can be sure that the spot sample is taken in the correct location with the correct procedure, that means the result will be good. When we compare the spot sample result against the GC result, we would expect a good comparable result. So if the result isn't comparable, there will be two possibilities. Either the pressure letdown system is not giving a representative sample, or there might be a spot sampling procedure that was done incorrectly. So what we're saying here is that if we have a comparable result, that means we will have a representative sample. So this is what we are doing basically. We got the spot sampling. Spot sampling have no lag time, and the data that goes into the analyzer has a lag time. So we, based on the previous GC surgery, we know how to calculate the lag time. So what we do here is basically we take the sample at a certain time on the spot sample, so we assume there's no lag time in there, and what we then do, we take the analyzer reading at the same time as the sample plus the lag time and plus one cycle of the analyzer cycle. So what we get there is basically a result of a reproducibility test, because we were basically measuring the same gas with two different methods. So what we do here then, because we are not really sure, sometimes the lag time can be plus minus 1 or 2 minutes, or probably more. We probably want to take the average of the analyzer reading and compare the result of the average of the analyzer reading against spot sampling. So basically the result is a comparison of the measurement of the same gas, which is a reproducibility test. Now, this is an example of a very good result. Basically, we take the GC reading, which is automatically taken by a conditional base monitoring tool software, GCAS in this case. And we basically take the spot sampling, and the spot sampling is taken at a certain time. So the dot that you see here is basically the spot sampling time plus the lag time plus the GC cycle time, and then it gets compared against the GC result. So what we do next then, we basically take the average of the data of this 4 data that happens, 1 data before the spot sample time, and then 3 data after that. So what we get here, the average of those data, and then get the mole composition, and then what we do is compare it against the mole composition from that particular spot sample. So what we get here is a comparison between GC average and the spot sample reading. In this particular instance, we got a very, very good data comparison between the spot sample result against the GC result. But this is not always the case. This is one of the cases where there is a procedure that was wrong when the spot sample is taken. So basically we got a little bit of air contamination inside the spot sample, and it's shown by nitrogen that is taken from the spot sample have significantly higher value than the average GC reading. The result of the spot sample comparison is only different in methane and nitrogen, but this is quite a high difference. So as you can see, the difference in the calorific value can become quite high, around 0.33%. Now, this is actually quite significant, but knowing that there is a spot sample contamination in the system, we then know that we need to ditch this spot sample result and then get the data from another spot sample. Now, the other place where we use this, when nitrogen is good, we don't see any air contamination. A lot of times we actually see heavy-end dropout, and especially in the North Sea here, because the place is really cold and then there's not enough heating done in the sample letdown system, the impact is the heavy-end dropout to the system on the sample letdown system. So what we tend to see is that the spot sample data, when compared against the GC data on the heavy end component, can be significantly higher than, so the spot sample data can be significantly higher than the average reading of the GC data, such as in this particular example, the spot sample value of hexane is actually double than the average GC reading of the hexane. Now in this particular example, the impact is quite significant. It's around 0.7% of a calorific value difference. So what we would expect from a comparison of this reproducibility test is that the comparison will differ within a tolerance that is stated in the ASTM D1945 reproducibility tolerance. Now, using this method, we have found more than 200,000 pound per month error because of the heavy end dropout. So the third place where we do a data comparison is by comparing two GC that measure the same gas. So when we go back to our uncertainty topic before, GC uncertainty is affected by 4 different parameters. The first one is the calibration gas, and then we got the calculation standard, which is for CV is the ISO 6976. And then we got linearity, and also we got reproducibility. So when 2GC measures the same gas and the calibration gas that is used to calibrate this 2GC is the same, then we can strike off the uncertainty from the calibration gas, because both of the GC will have the similar uncertainty. And then also we can remove the calculation standard uncertainty, because both of the GC use the same calculation standard, and then we can assume that the GC will be running in their linear range. So the only thing that affects the uncertainty on the GC when we do a comparison on the data is the reproducibility. So what we know is that from the GC manufacturer, normally reproducibility or repeatability, they always state that the GC can operate within plus minus 0.05%. So what this means is that we would expect 2GC that measures the same gas will have a CV result that differ between each other by plus minus 0.05%. So, and this is basically the expected reproducibility of the GC, and this is what we would try to achieve in 2GC that measures the same gas. Now, let's see the impact of the reproducibility test that we have when we compare a result of 2GC. So if you can actually see this result here, the 2GC actually giving not too much of a difference in the result. We got a failed result on methane and on heptane, but if you see the difference on the mole percent, the tolerance is only out of the tolerance by a tiny little amount. So it's pretty much almost in the border of its tolerance on methane and heptane. However, when we see the actual CV difference, we get a CV difference of 0.486%. Now this is actually worth around 48,000 pounds per month, which is around 600,000 pounds a year. It's quite a lot of money to be lost here. What happened here, that there was a valve timing issue that wasn't accounted for by calibration. Now, we only detect this because we did the data comparison. What happened here is that we have an isomers, in this particular case, cyclohexane, that is not exist in the actual calibration gas. So what happened here on the GCA, some of the cyclohexane got transferred across to the heptane. On the other GC, all cyclohexane is measured as cyclohexane. Now, also There's also a little bit of a mistake where the cyclohexane isn't accounted for by the flow computer at all, and therefore we basically got a proper mismeasurement on this particular component because it's not really accounted for in the overall calculation. Now, because we do a data comparison, we can actually see that there might be something wrong in the system. So we can actually go into more detail of the configuration. So when we correct the valve timing and make sure that all the composition is detected, we can then compare it again, and we can see that the CV difference went down to 0.037%. And because it's within the reproducibility limit that is stated in the from the manufacturer standard, we can assume that this difference is actually quite negligible. However, when we see this particular difference, actually say 0.037%, it's not really far off from the actual limit of 0.05%. But when we see the actual composition difference between the two results, if we take the average on the next slide, we can actually see that the difference between GCA and GCB is really, really small. And if you see the difference here on the mole percent, for instance, on methane, is only half the actual limit. And every single individual component have a very, very far away difference in comparison to the actual limit mole composition. So what we are saying here is that the ASTM D1945 standard, I don't really think that it can actually be used as a comparison standard for the two GC measuring the same gas. It's all right to actually perform a reproducibility test in comparison between spot sample and the GC reading, but when you actually have two GC calibrated with the same gas, the same calibration gas, we need to actually work based on the CV data comparison rather than the STM D1945 limit. So what caused the difference here? As I said before, some isomers are not included as part of the calibration gas, so it leads to faults in valve timing. Is unaccounted for by calibration. And this is one of the important things actually to make sure that we have the right calibration gas for our application, and also the right system to ensure that every single gas that exists in the calibration gas or also exists in the process gas that needs to be measured is measured, and the system that is measuring that is capable of doing that. The issue that we have here before is that the cal gas have a cyclohexane in the calibration gas. It also has 2.2 dimethyl butane in the calibration gas. However, the flow computer doesn't account for these two particular isomers, and therefore it creates an error in the system. Now, the drift in the system gets bigger because GC haven't been calibrated for a while. This is another cause for the difference. And this happens in some of the case study that we have where a GC is validated most of the time. Now again, the validation is normally compared against a standard that has quite a high tolerance. So a lot of times the validation passes, but when we compare the result of the CV between the two GC, it can have quite a significant difference. And there's nothing wrong with the validation, but what we want to do is that if we actually have quite a high difference in the CV, then maybe it's time to perform a calibration on the GC. The current procedure that we have been seeing in many operators is that validation happens all the time, and when it passes, the GC is left alone until the validation actually fails. Now when validation fails, then the GC gets calibrated. Now there's a fundamental issue with that particular logic, because if the validation failed because of the calibration gas quality that has been deteriorating, what we then do, we calibrate this with that particular calibration gas and accept it. We basically introduce even bigger error to the system because we calibrate it with a fault calibration gas. So therefore, if we want to do the validation, whenever we have a failed validation result, the first step to do is not calibrate the GC because of the validation fails. The first step is to identify why the validation actually fails at the first place. Now, the other cause of the difference is that GC operates in its nonlinear range. Now, this happens a lot due to wrong calibration gas composition selection. Now, when the GC operates in nonlinear range, no two GC actually have the same similar nonlinearity property. So if the calibration gas design is wrong, such as the calibration gas composition is far away from the actual gas composition, we can get an impact from the nonlinearity of the detector, and the result is basically bias in the measurement. So the bias on the GCA and the GCB might be different, and we basically have error that can be unaccounted for. It can also be quite big. So in continuation to that nonlinear range, then it's also important or also good to be able to compare the single point versus the multi-level calibration mole percent. So what is the risk from having wrong calibration gas composition? So when we perform ISO 10723 performance evaluation test, we will get a report, and in the report it will show the maximum bias the GC can produce based on the operation range that we provide. Now this is why it's actually also important to provide the correct range that we operate on our pipeline. A lot of times it happens in many occasions that the range provided by the operators to the ISO 10723 provider is much wider than the actual composition that the pipelines actually operate on, and the result is a lot bigger bias than the actual range of the pipeline that we actually operate on, because we actually work based on the Monte Carlo simulation based on the range that we provide as an input to the Monte Carlo simulation. Now, based on the analysis function, we can actually then, rather than doing a Monte Carlo simulation, we can then analyze individual composition bias from our gas composition. So if we actually have a GC that measures process gas, we can basically get the single point mole composition, we can also get the multi-level calibration composition, and then we can compare them. So therefore we can actually get the individual composition bias of each component, and therefore from there we can calculate the CV bias of each individual analysis result. So based on this, then we can actually determine what will be the best calibration gas composition for the pipeline composition that we have to ensure minimum bias. Now here's an example. This is the impact on bias when we basically have a calibration gas of this particular component. Now if we actually operate between the range of 60% methane to, let's say, 90% methane, this is what we can expect of the range of the bias. So if we operate at around 85%, we will be sure that every single component, any single possibility of the component that we have will fall in on plus minus 0.02%. So this particular setting works pretty much between 80% to 90% of methane, which is in a good operational range. But as we go to a lower range of methane, such as 65%, the bias that we can get from the measurement, it can go up to 0.12 megajoule per meter cube. Now this is quite a significant bias. Now if we actually operate, let's say, on 70%, we don't really want to have a calibration gas such as this. Now if we now have the calibration gas that sits at around 70% on methane, this is the bias distribution that we have. So on the 70%, we will have plus minus 0.02%, and it can work pretty much on this particular range where between 70 to 80% is probably still okay, and the bias distribution is pretty much good. Now, depending on what kind of a bias we would like to accept on our system, then we can use this chart to actually operate on. If we actually have a bias tolerance of, let's say, 0.06 megajoules, then every single this calibration gas can be used in every single range. But the best way is actually to implement the multi-level calibration constant. What it means is that all this particular bias will all drop to 0. Now, this is the gas range that we use for the ISO 10723. A lot of times, the gas range provided by operator is not the actual pipeline operator range. Now, this is one of the examples from the ISO 10723 report when we actually have, for instance, methane is assumed to have a range between 78 to 98%. In actual case, it's only 88 to 94%. Nitrogen is assumed 0 to 9.8%. In actual case, it's only 0.7% to 5.2%. So all individual values here, even ethane here that goes between 0 to 12, in actual case is pretty much between 3 and 4. So it's very short range. Now, when mole composition is taken from the actual pipeline range, the bias result can be very different in comparison to the assumed range. So this is the bias impact on the composition range, the example that I gave you just now, which is between 78 to 97 or 98%. You can actually see the error distribution here. When we get on the 78%, it goes to minus 0.1 megajoule per meter cube. Now this is the assumed range. So this is the bias impact on the actual range. If we actually use the actual range from the pipeline, the bias on the 10,000 data that I simulated with the Monte Carlo, every single one of them falls in within 0.02, plus minus 0.02. It's probably less than plus minus 0.01 on this particular case. So therefore, when we actually operate on this particular range, there's nothing really to worry about, because the GC will pretty much be operating all the time within its linear range. So this is the actual implementation. If we basically have a mole composition trend, and this is the actual mole composition trend, we can then compare it against between the multi-level calibration mole percent against a single point calibration mole percent. So if we basically have mole composition, the true mole composition of the average of 84.994, but we have a calibration gas at 69.5% on methane, here's going to be the result. We basically have minus 0.24 mole percent bias on the methane component. So rather than reading 84.9%, it reads 84.75%. So when we see the impact on the CEV comparison, we then get a difference of 0.047% in the CEV, which is quite a big difference in the CEV, although it's still acceptable. However, if we change the mole composition of the calibration gas to somewhere closer to the actual mole composition where we actually measure it, we can then see the difference. Now we only see minus 0.07 mole percent over bias. So instead of reading 84.994, it's actually reads 84.92% on methane. Now the impact on the CEV is now only 0.013 rather than 0.047%. Now this is really negligible. Now this is what I was saying, that the data comparison will allow us to design the right calibration gas composition to be used for that particular pipeline. In conclusion, data comparison provides a very powerful tool, first to ensure that the GC works within its tolerable limit, and then it provides a tool to validate pressure letdown system by checking the spot sample result and compare it against the GC reading, to design calibration gas composition based on the nonlinearity property of the GC, to determine the risk from the nonlinearity by comparing the single point calibration mole composition against the multi-level calibration mole composition. A lot of errors have been found and corrected because of the data comparison was done. Some of the examples are we've identified that some isomers not being detected, and we identified issue with the heavy end dropout. We also identified validation or calibration issue, and a few other issues as well that have been detected that's not been covered here. So as the conclusion of the whole GC surgery, what we have discussed is we have discussed how the GC works to begin with, and we have discussed how to interpret the GC calibration data, and from there how to record and monitor the historical data using control chart, then how to quantify the control chart into an uncertainty value that we can actually use to analyze the GC performance over time, and then the bias due to nonlinearity of the detector, then how to calculate the lag time calculation, and today we talk about the data comparison. All in all this topic we talk about is to ensure that the whole analytical system is working properly. Pressure letdown system, the GC, the carrier gas, the cal gas, also the people that perform the maintenance on the GC. So all in all, it's basically to ensure that the GC is maintained to provide the best measurement accuracy all the time. So we hope you have found this session useful, and if you do have any questions, you can then post the questions into our GC surgery group, and basically I'll try my best to answer that. So this is basically the final session of the GC surgery. Thank you very much for watching, and we hope that there will be some other sessions, probably not on the GC surgery tag, but we hope to see you again for a different event in the future. Thank you very much. Thank you very much.